One thing you have to be careful though, and this is going to be sort of part of the next assignment, one thing to look out for is if you have dispersion errors, okay, these overshoots may kill your stability if this, the maximum velocity basically here in the numerical solution is greater than 1. So the overshoots may make it go unstable if you're not careful. Okay? So we'll discuss that more with respect to the next assignment as well. Okay, now this is MacCormack's method. For MacCormack's method, I'm showing you here 3 solutions with different CFL number. This is well, I think this is supposed to be a 3, and I'm just not doing it correctly. MacCormack's method was our 3rd step for assignment number 3. It's got the same stability requirement, but we see here again that the oscillations for this 2nd order method increase as you decrease the CFL number, the same as the previous one. However, which one is the best was the question for this assignment. Here is the MacCormack method. Now I'm showing you MacCormack method for the CFL equal to 1, which is the best CFL for this method, at different times. And you can see that it behaves quite well, right? So, which is the best one? MacCormack, right? Yay. Alright, so that's up to step number 3. We got 2 more, right? 4 and 5. So this is what another of the mysteries that we had in this assignment, which is we had the implicit beam of warming method with without damping, and a lot of people were observing this weird drooping here on the left side of the solution, right? This is the way it's supposed to look, of course. This is the way it was looking for a lot of solutions, right? Okay. Not good. So, there's a lot in this slide, so let's go by parts. So, the final difference equation that you had for this case looked like this. You had basically, here are your unknowns, right? The unknowns are at time n plus 1. So these are your unknowns. These are the unknowns. And then these are your coefficients. So you have a tridiagonal system where these are the coefficients. So you can write this in this form where these are your coefficients. This corresponds to this term over here. This B is simply equal to 1, right? And C is equal to this over here, C1. And this is equal to D1, right? For the general tridiagonal system. So many of you went and looked up the Thomas algorithm for solving tridiagonal systems. How many of you looked this up? So we're going to see better show of hands. 1, 2, everybody. Everybody? Good. Everybody. So if you went to the Wikipedia entry for the Thomas algorithm, you will find that they showed the matrix form of this system that's written right here, like so. And they said, well, the algorithm works by forward elimination, which basically eliminates the lower diagonal, and then backwards substitution, because obviously if you make all of these, this lower diagonal, you make them 0 in your system, you can solve the equation for xn, which you can back substitute and get all the subsequent values, right? So this is the 2 steps, forward elimination and then backward. So this is backward substitution. I used the wrong word. So it's just a specialization, substitution, of Gauss elimination for the case of a tridiagonal system that works at order n. It's great because Gauss elimination is order n cubed. So it's a lot of work, order n cubed in the sense that you need to do n cubed operations to solve for n unknowns. In this case, tridiagonal system, you get the answer in order n operations. So that's good. So this is what you saw in basically any of the sources that you find online for the Thomas algorithm. Looks like that. I don't know if Wikipedia is the sort of essence of every other article on the internet, or everybody else copies Wikipedia. I don't know. It's a chicken and egg problem, right? But if you were to read carefully your Wikipedia entry, you would have noticed that it said that they assume A1 equals 0 and Cn equals 0. Because in this matrix form, A1 just doesn't appear, and Cn just doesn't appear because it's, you know, you want a nice little rectangular matrix, so this guy sort of sticks out there. What do? So it's assumed that the first value of A is 0. But that's not our case, is it? Right? Okay. Furthermore, we have the issue of boundary conditions. So, what do we have? So the question that we have is, what if A1 is different than 0, which is our case. In fact, Cn is also different than 0. Could have, or it could be different than 0, right? And plus, we have a boundary condition. So let's look at that case. So what happens is, really, that we want to use the Thomas algorithm for all interior points, but we have boundary conditions. So if we define, for example, we define, say, if we want to have boundary conditions at I equal to 0 and I equal to n, say, so these are try to make it a little straighter. These are our boundary conditions at 0, then we have 1 and so on, and then we have a boundary condition at n, which happens to be equal to 0, so it didn't affect very much. But here, the boundary condition was x, so x0 equal to 1 was our boundary condition at this point right here. We had to be able to impose that, right? Okay, so what happens is that we want to use the Thomas algorithm for a system that looks like it looks like 1 for the boundary condition. The first row is going to be 1, 0, 0. Then we're going to have A1, B1, C1, 0, and so on. Then we have A2, B2, C2, and this value is 0. And then we have 0 down to the right, and 0 all the way to here. And the diagonals, these are our 3 diagonals. And the final one is going to be Cn. And then we have, I'm just going to leave up to Cn because we really don't need to worry about boundary condition there. But let's suppose, in the general case, you could have a boundary condition here also. So let me just write it for a more general case. I'm going to write this as B0, and then on the other hand, I'm going to have xn equals bn for boundary conditions, okay? So this guy is going to be 1, and then I have a 1 here, 0 all the way there. These are our unknowns. I'm going to put u0. This is equal to, of course, u0 is equal to the boundary condition at that point. So this is 1 times u0 equals v0. There's no equation there. There's no unknown, but we just put it on this matrix because that way we also have a1 doesn't disappear. u0, u1, these are our unknowns all the way to un, and I've called it n plus 1 in my notes. Let me be consistent with that. Because it's going to disappear anyway in our case. And un plus 1. So b0, and this is the right-hand side of the equation we called, in the algorithm, in the Wikipedia entry, we have d1, d2, up to dn, and then we have the boundary condition n plus 1. Right? Does that make sense to everyone? So for all interior points, we have the system as it appears on our Wikipedia article, but we've added a line in the matrix for the boundary condition at the left and added another line at the bottom, another row for the boundary condition at the right. Does that make sense? That's the real system that we are solving, where of course this is known. We know this guy. And we know this guy. So what do? We basically can bundle and move the boundary conditions to the right-hand side and write the system as follows. We can now write, so bundle to the, so move the boundary conditions to the right-hand side, because the first equation is going to have A1 multiplied by the boundary condition equals and blah blah blah. So the first equation is A1 x I called it U. A1 U0, the boundary condition, plus a B1 U1 plus C1 U2 equal to D1. That's the first equation really, because A1 is not equal to 0. Okay? So we need to move it to the right-hand side. So we write now B1, C1, 0, and now it looks like all the Wikipedia articles. A1, B1, C1, and we have U1, U2. I'm going to eliminate the last one, 2, up to UN, and then we have BN, AN. This guy is CN minus 1, 0, and then these are my 3 diagonals. And our right-hand side has changed to have D1 minus A1 boundary condition 0, D2 all the way down to Dn minus 1, and then we have Dn minus Cn Bn plus 1, the boundary condition at the right. For our case, this guy was 0, so it didn't affect anything on the right, okay? But this is the general case. So there is a change on the right-hand side to account for the boundary conditions. That's the take-home message. It's crucial to take care of the boundary conditions properly in implicit methods. This thing happens right here. Okay? So what happens in our class assignment, of course, this term, this B0 was equal to 1, and this value had a number, so this existed in our class as in the assignment. And this one was equal to 0 in the assignment, so nothing happened on the right-hand side. We didn't have a problem there. We don't have a problem on the left. Okay. So let me show you what the code really should look like. So here we have, can you see this? It's a little small. Well, you can still see it, right? So we have, say, 41 points, which gives me that we're looking for delta x equal to 0.1, which is the value I gave you at first. And I'm going to do Quran equal to 1. Fine. Here's my damping coefficient. So no problem. I'm printing the x and dt just to know what I'm calculating, so no problem. I'm initializing a bunch of arrays here to 0. And I'm doing everything double because I'm calculating the damped and the undamped in the same plot. So that's why I've got everything twice. Here are my initial conditions. Right? It's just equal to 1 between 0 and 2. everything was initialized to 0 before, so I only have to change the values between 0 and 2, and that creates my initial condition. So, first of all, you notice that I've got here a definition for A1. I'm calling A1, B1, C1, and D1. That's the full array for the undamped case, and then I have A2, B2, C2, D2 for the damped. So I have everything twice in my calculation, 1 and 2 for damped and undamped, or the other way around. Right? So I'm going now to get all the values of A, this is just A, which is minus dt over dx divided by 4 times un at I minus 1. But I'm starting not at the, so basically the indices here go from 0, okay? So when I put a 1, I'm skipping the first step. And I'm skipping the first element of this array. So it's a little bit different than what you see in the ones that did in MATLAB that start, the indices start on 1. Here the indices start on 0. So my first term of the array has index 0. I calculated it separately in the, with the boundary condition here. Okay? And all of the values of B are equal to 1. All of the values of C are, here's the values of C, dt over 4 dx, u and I plus 1. All of the values of D, the right-hand side, are equal to un, except I have to modify the first term. Here I'm modifying the first term to take into account the boundary condition. Okay? Here, basically, this is just auxiliary variables to keep my diagonals, which are going to be changed because I need to use them again in the next time step. Okay, so that's the only reason I needed to add this, because they're modified, so I want to recover them. So inside the equation, I'm using these C12. Sorry for the not very, this is a sort of cryptic naming of the variables, but I'm trying to explain. These are just my diagonals, my diagonal C. I didn't do anything for B because it's just one. C and D, the right-hand side. Again, for the right-hand side, I've got, let me see, I've got everything. Okay, here these are the formulas of your Thomas algorithm, right? But, okay, I don't think there's anything else to explain there. This is the key here, that the value of A1 is not equal to 0, and that I modify D for the first element by this quantity, right, which takes into account the boundary conditions. So let me just run this. Let's see, what do I have? I have delta x equals 0.1. This is the final time, 1.8. And so that's decent. So I can run this. What's it called? And we have on the left, it's perfect, like it should look. And of course, the undamped has a lot of oscillation. The damped has much less. Okay, the final time is 1.8. The delta x is 0.1. Now, if I were to comment out this line right here, this line, which tells my code that A1 is not 0. It would be 0 because I've defined everything 0 at the first. So I'm just going to comment this line out. Okay? Save it. Run it again. But I didn't comment. I've got the whole code repeated for without damping, and then I have it with damping. And I'm leaving it here without without uncomment. I'm just going to comment that line for the without damping. And let me just advance a little, just a few time steps. Let me take just the first 4 time steps or something like that. 0.4. Okay? So we can see what happens. So this is the first 4 time steps. You can see I've only commented 1 line for the undamped case, and here we have our droop for the undamped case. Whereas the damped one is perfectly flat there like it should be. Right? And if I only uncomment now this same line, that's all I'm doing, and I run it again, everything's flat on the left, like it should be. So what would happen, for example, if I use a much smaller, let me see, now I can use, say, 81. I'm going to comment out this, I'm going to use 81, so let me just run it like that, so you just see that it's working perfectly. Although as it gets, you get more oscillations on the undamped case, so that's going to, eventually it's going to blow up, the undamped case, because of all these oscillations, okay? But it's nice and straight on the left. So now I'm going to just comment out that line here that defines the value for A1 so that it's remain being 0 as initialized. So I'm going to comment out both the damped and undamped cases. There. And we've got that thing on the left. It looks pretty ugly, right? Now, what happens if I advance the same solution for much longer time? Say, what happens if I do 2.0? Let's see what happens. All I've changed is the time, right? Look what happened. Because once that stuff, bad stuff, moves to the right, it contaminates everything. It makes my undamped blow up completely, and the damped has now these things, so it's completely ruined, right? So it doesn't really stay there on the left. Now I'm going to keep all my parameters the same, but I'm going to again uncomment the line that defines the first element of A for both damped and undamped cases. The undamped blows up anyway because the oscillations are too big, it blows up. The damped one looks nice and flat and much better. All right? So several things. Also, we note that as we decrease the mesh size, the undamped case blows up because now this will increase the oscillations, right? The reduced mesh, if it's a more refined mesh, we will have bigger oscillations, and those oscillations in the end make the whole thing blow up. Okay? For current equal to 1, for a smaller time, let's see what happens with 1.5. Still blow up for the undamped case. About to. Actually, you can see how big the oscillations are. It was still able to continue working, but these oscillations are huge now. So it's about to. So that is the reason. That is what happens with this boundary conditions issue. Now, what else do I have here? I have two cases with, well, again, the two cases with different resolution. As you refine the mesh, for the same values of the Courant number and the same final time, we see here that the undamped case basically blows up because the oscillations are increased. So the correct take-home message for this beam unwarming, implicit beam warming scheme was that even though the implicit scheme is unconditionally stable, if we do not add any damping, these dispersive errors are so large that it will eventually blow up anyway. And with damping, we have the issue that the damping itself is explicit, so we lose that theoretically nice property of the scheme being unconditionally stable. Now we have an explicit part to it, so it becomes conditionally stable, but it fixes these dispersive errors. Any questions?